Okay, we're starting. Good morning. Only one in the class today. The other one will be watching the video later. I'm just going to start off by saying that I did finally get started grading again. It's just taken me a while to get to that. So it's underway, but I don't have any results to give you at this point. I'll post them into Slack. Things just keep me really busy. And this weekend, because of the 3G or 5G project, 3GPP, Third Generation Partnership Project, which drives part of 5G and OFDM. I was studying that, and since you're here, Joseph, I was on a team call on Friday, and Keysight test equipment is kind of right in the foreground because this project is launching and they're wanting to buy some expensive 5G test equipment. And I said, oh, I have a student in my class that's working in another area. He works here locally, and I spent a bunch of time looking at some of the app notes and things that are available for the vector signal analyzer, which is something that applies to this class, and some of the other things. The application notes are pretty helpful because they also extract some of the information from the standard, which makes me relate now even better to the project you're going to do, Joseph, with the PCIe. It's like
Keysight tries to get on the standards committees so they can offer them in their products. It's pretty common.
Yeah, but I mean the standards documents are just for 5G. It's just massive amounts, and we just wanted to know some of the properties of the OFDM modulation. We'll be getting into orthogonal frequency division multiplexing, or modulation / multiplexing later in this chapter. So it all kind of relates to that stuff. Plus there's a DSP aspect to it too that I'm working in that has to do with undersampling and picking the right Nyquist zone and then getting the right amount of rejection so interference doesn't creep in. I mean, simply put, DSP and communications theory and digital, the whole thing is just it's all together. It's not like you can just say, I'm going to do this void of that or do this void of that, because if you're going to be involved with sort of the whole picture, you're going to be doing that. Okay, two things that I did since we last met. I reposted the problem assignment, and nothing really startling, but I did put this in as you suggested, Joseph, to have 20 bonus points. I haven't had time to resolve the issue on that. I played with it some more. I've worked on a bunch of Python stuff, but I haven't spent a serious amount of time. One thing I'll just point out, since we're looking at this, whenever I've done equalizers, there's something that's in the equations that sometimes escape me and I don't quite see everything. So I'm just going to jump over here to one of these examples. I'll take the one that's down the page here, the standard decision directed type. This right here, though, is the update equation for the least mean square algorithm, and we talked about it in class. Whenever you implement it in code, because we're dealing with complex signals, that conjugate on the states that are being held for the FIR filter that's the equalization filter, those states are complex. And a lot of books, when they talk about adaptive filters, assume it's a real signal, and maybe that PAM4 is, you won't have anything but a real signal samples. But when you have complex, then it's the conjugate gradient that we're doing. This stochastic gradient is a conjugate is needed in there. And if you don't have the conjugate here, or if I conjugate somewhere else and then I end up conjugating a second time, the algorithm never converges. So I always bump into that, and I have to just be really careful, and that could be part of it. I mean, Okay, in this particular scenario, and this is what I haven't drilled into, so I'm just speaking this out right now. If you load this in your back brain for later, this is something that I haven't explored enough. I messed with it a little bit, but because of the way this filter is a concatenation of the precursor portion, which is complex coefficients, and the postcursor, which comes after the hard decisions are made, the slicing is made. In the case of BPSK, which is the way it's coded up right now, that slicer output is just real valued. It's just, you know, exactly. I did put in my code though, just to see how this would unfold for other types of modulation. And I did this kind of as a placeholder for me, so if I wanted to come back, I could, I'd be set to do that. It's this area right here. I defined an array called constellation, which right now just holds plus and minus 1. I defined another constellation for PAM4, thinking ahead, that holds constant values of 3, 1, minus 1, and minus 3. Those would be the 4 levels. And then you can see I also defined another one for QPSK, which would hold values at 0.707, well, a radius of 1, but values of 0.707 in the real part and the imaginary part in all 4 quadrants. So that is a complex baseband constellation. And then when you're doing this minimization, and I won't go into that right now, then that works. But going back over here to what goes on in this filter, I stack up the states right now as being the precursor states and the postcursor states, which it's possible that there's something going on in there. And that's what I don't know. I mean, I have to investigate that. And sometimes what you have to do when you're writing these algorithms out, you have to kind of back up a little bit and take a simpler case, or just maybe make everything real in the filter, because really, well, the channel is real in the model that I've done. So it could be that the complex values are causing confusion. You have any feedback? Thinking about that?
I guess I'm thinking, when you have complex baseband, I guess the main point of having a complex filter, right, is so that you can filter the stuff below FC different than the stuff above FC. Right? 'Cause you're mixing FC to 0, correct?
Yeah.
So, but if your response is symmetric around FC, then you can use a real filter, right?
Yeah. But the point here is that we don't really have any information we're trying to equalize to. We're not trying to, in the case of this constellation, the channel is real, so it is symmetric, and it's not going to rotate the constellation one way or the other. So one of the things an equalizer filter can do, if the constellation comes through the channel and gets twisted slightly because of complex channel coefficients, which are absolutely the case in a real mobile radio channel, the equalizer will not only equalize the impulse response to look like, you know, a delta function or something, but it will also, it handles other things. It rotates.
Like a non-constant group delay.
Yeah, it can do neat things for you.
Butterworth has a non-constant group delay.
That's right, but
So
we're not sending any information. The channel is purely real. So I guess what I'm getting at is there could be something here that is causing some confusion, and then the conjugate, you know, is still, it's still down inside of here. I still have it, and I found out when I was tweaking with it that NumPy actually has 2 different names for conjugate. It has conjugate spelled out, and it has CONJ. So I was thinking, did I miss something? Because I've used CONJ a lot, because that's the same terminology that MATLAB uses, but that didn't make a difference.
how do you initialize your feedback coefficients? Do you initialize them to all zeros? Or?
I'm initializing them to, in this fashion. The precursor values are zeros, the on-time value is 1, and the postcursor values, and these values are held in the decision directed or decision feedback register, those are also zeros. So I don't want to go into debugging it. We were looking at it last time, but I'm mostly talking about this because this little thing, a conjugate, can make the total difference in the world. If it's not conjugated, or if you conjugated it twice, then you've unconjugated it. Or if half of it is, if there's something mixed up in there, because everything seems sensible to me, but it's not converging. And I've seen that happen many times in the past. If you've never experienced that, and I wouldn't expect that you would because you haven't done equalizer code before, it's just like, wow, that mistake kills me. And in MATLAB, it was always the dot prime symbol that you would use at the end of an array in MATLAB to conjugate or not conjugate, because in MATLAB, if you transpose, you always would conjugate. And if you wanted to do a row times a column, to do it like an inner product or something. So little things like that over the years have zapped me countless times, and you just, you're buzzing along, and then you're having to resolve bugs like that. So just thought I'd point that out. The other thing that I did that you should have seen by now, but I'll just go look at that really quickly, was I decided to give you just the pages from the Barry, Lee, and Messerschmitt digital communications book, the entire chapter 9, which is all on adaptive equalizers, just so you'd have the whole thing, so you could look at it if you wanted. That single shot I gave you was only one page, so you could just see it, and it might be useful. I can't really say that I'm totally on above the boards with the copyright, but I'm only giving you selected pages out of the book. Chapter 8 is very long in this book, and it's entitled Equalization, so it goes really, really in depth to theory. It starts with the fundamentals of equalization. It goes through a technique to look at how you can equalize a channel and what can you attempt to get theoretically, and it's called water pouring, and I can't explain that really well because I haven't reviewed it lately, and then it goes into the history of equalization with zero forcing. It spends a lot of time on zero forcing, so you won't see any zero forcing in this chapter 9 because it's all in the fixed equalization. Because remember, zero forcing is you get the channel and then you apply just the math to it, and then you have a set of coefficients. So they don't call that adaptive equalization, so that's in the preceding chapter. The book is actually very good. I was looking on Amazon to see how expensive it is right now. It's $225, so it's kind of expensive. The third edition came out in 2013, and John Barry is at Georgia Tech. Lee and Messerschmitt are at University of California. Let's see, school that's in San Francisco. I'm drawing a blank. It's not Stanford, but what is the other school? Well, maybe it is Stanford. At any rate, the chronology there kind of is youngest to oldest, and I think David Messerschmitt worked at Bell Labs originally, and he was probably involved with adaptive equalization for telephone lines. I'm not even sure if he's living anymore. I really don't know. All I know is that when books are written, and the first two editions just had the last two names on it, so frequently when a book comes out as a third edition or a much later edition and a name is added up front, it means first off that author took the primary responsibility of publishing the book with more info in it. And it also frequently means that one of the last name authors might now be deceased. Maybe you've noticed that before. I've certainly seen it before. Like,
I have no idea.
I mean, that's just the tradition, I think, the way things work. Like Roger Zemer has several books, and he's deceased now. I didn't want the job of saying you can have the book and you can write a new edition if you want to. I don't really know I think it just, at this point, all his manuscripts or whatever, just, it's over with. Both he and his co-author on some books are deceased now, so that's the end of the lifetime of the document. You probably never thought about that, but I certainly have, because I wonder sometimes, it'd be nice if somebody would publish a new edition and then lo and behold somebody stands up, which I believe was connected somehow or another with the original authors, and somehow or another something happens where they take over, and I don't know how that works in the legal side of things, but to me it's a little bit interesting. Okay, so.
Would it be the case that, so you said all of that homework is due a week from today, right?
I did, yeah, I can make some adjustments. We are running down on the semester though, so.
Right. I was gonna say, even if you.
I can let it slide off. I don't have a problem with it, as long as if I give out new stuff, I'll be giving out another assignment for this chapter, and then we'll move on to the end of the semester's material. We'll move on to the other chapters, but there is.
Or I was even saying if you could extend the deadline on the bonus problem.
Oh, definitely.
Like, and just say,
It's just an open problem.
Yeah, if I hand in 1 to 5 next week, but I can have a longer deadline.
Yeah.
To look at the extra credit.
Yeah, that's fine. My intent originally was if I could have gotten 6 working, I was going to use it to replace number 3.
Right.
That was my original thought, but
I guess I just don't want to rush that problem.
now I don't want you to either. We do have to have an in-class exam, which is pretty much based on what we finished off with the last chapter, and that has generally been 2 weeks from today. It's generally been the Monday of Thanksgiving.
You said you weren't sure you might have made it, you were thinking of making it take home, but you
Yeah.
weren't sure.
Yeah. I think I might just do that because it's easier for all of us. I won't have any classes to go teach that week. Probably what I would do is, if I go that route, which seems reasonable, I have to have a take-home exam in my other class, DSP class, on Friday. If I was to do it for this class, I would probably post it by Friday, and then I might just come over here at 8 o'clock on Monday to see if there's any questions, or just see if there's anything anybody wants to talk about, and then not hang out because you could just be working on it or something like that. I'm not making a firm decision on that right now. I'm going to be mulling that over, because now is when I start to go into a bit of a panic mode where I look at how little time there is left. There's 5 weeks of classes left right now, if I'm thinking right now. There's 4 weeks of classes left right now, plus Thanksgiving week, which is just a half week. So, but we have 5 more class meetings for this class. So, and I do have, there's a lot of stuff that I could do. So, let's go do it. There's some fun stuff, and this right here is one of my favorite topics. I think Dr. Ziemer really loved signal space modeling for digital communications, because I know who was his inspiration. A book that's on my shelf that he had me buy a long time ago. Those authors are definitely deceased, but when digital communications was coming into being, people that were very theoretically oriented wanted to try to do a lot with mathematical modeling, so they decided a whole class of digital modulation theory could be put up into a signal space form. And then once you have it in a signal space form, then it sort of parallels exactly what goes on in statistical decision theory, which is what I teach in the other classes. There's a section on that in the statistical signal processing class 5615, but it originated from the detection and estimation theory class using the book by Van Trees, and my notes when I teach the 5615 are from Van Trees. So that was a question I think you had. What do I do with that? And I use that book. And the statistical decision theory is, like one half of data science, machine learning type stuff, where you're either detecting, making a decision about hypotheses, or the other half is estimation theory. And that's.
You said you wouldn't do that next semester, but you might in fall 22.
Yeah, I could do it for you just as an independent study. That's how I would do it, because I don't believe I'm going to be officially staying. I'm going to try to negotiate some spin down thing, but some of the.
You would do it in the spring.
This spring?
Yeah.
Well, if real-time DSP doesn't get anybody and I have to do something else, I don't really know. I'm already getting a buyout for one course. It's something that I've had on the shelf for quite a while, and I have to use it. I just want to use it, because if I never use it and just work myself even harder, I'll say, I had that sitting there, no one's going to give me anything for it,
Right.
so I need to use it. But if somebody like one person is taking it, then it's more manageable than doing it in a classroom like this. It would just be an independent study. I can get the course set up so you could take it under the course credit or the course number, but we would never meet in a classroom. It would just be a meeting in my office / virtually.
Right.
And sometimes when I do that, I also invert the class, so I have the person actually work the problems for me, and then I critique it. There's actually no lecture, because I have the old videos and I have all the lecture material. And that actually works out really well. That format does. I could have been doing that in here, where I just don't lecture, you work the problems, I divvy them up between the two of you, and then you work them in front of me on the whiteboard, and then I critique them, and then you get to go back and polish them up and turn them in later. That works actually really well. It's called the inverted classroom. There's a technical name for it. It's not turned upside down, it's rotated, I guess, front to back or something. Okay. So in coherent communication systems, it's possible to do this representation conveniently, and then we can add the synchronization aspects on later. So the idea is using a set of basis functions, these phi sub j's with coefficients a sub ij, to represent a set of signals whose number is k different symbols, out of a maximum of m, that can be used, k dimensions, I guess. K dimensions less than m, the number of basis functions. So what does that mean? Well, that goes back to linear algebra. If you have m dimensions, we could signal, we're going to think about signaling using all of those dimensions for our different symbol types, or we could have it be less than those symbol
I was
types.
going to say, I guess, doesn't this kind of look like linear combinations in a matrix, basically?
Exactly. So we wouldn't want to have one signal type be a linear combination of another signal type, or at least we wouldn't want to have them lie on top of each other. So.
Right. I guess you can talk about like the rank of your signal space matrix and all that.
Yeah, you're right. So we're assuming that these phi functions are orthonormal over the symbol interval, which our definition of orthogonality is using the integral as an inner product, so the integral of the product of two basis functions over the symbol period. And this notation on the left-hand side is just a notation I've seen when I've taken math classes, the angle brackets, and then the comma to say these two things are inner product. And for complex functions, the only thing you have to do is you have to put, the conjugate on the second one. And if you look up in chapter 11, it talks about how you could find the aij's, It's actually called, not because I haven't been thinking about this. It's projecting and right now I'm drawing a blank on that. I guess I should look in the book. It's something that you had in linear algebra though. I think that's the right term I'm thinking for. But since you have the book, what I'm saying is you can go look in chapter 11 and then you can see a more generalized approach to all this stuff. Okay. Well, Gram-Schmidt. So I'm thinking of Gram-Schmidt orthogonalization. That's kind of connected into this, and it's not quite the same thing, but Gram-Schmidt orthogonalization is where you have three different functions and you want to find a set of basis functions to expand those three over. And that's something that I think you still do in linear algebra. Does that ring a bell? A Gram-Schmidt procedure.
I don't remember.
Yeah. It's like if you have a vector in 2 dimensions and you have one that's along the x-axis and one that's somewhere in between, then you would say, okay, what do I need to represent these two? I'm going to use the very first function is, in the orthogonal expansion, is the first function that first phi function, and then you project the second function onto that first one, and then you say, okay, this component is on here, so I remove that with this projection, and then it's the orthogonal piece, and then that forms your second basis function.
I guess it's kind of like diagonalization, right?
Oh, yeah, diagonalization in that you're doing a rotation in order to get things to project into orthogonal components. Okay. So the way you can visualize these orthogonal functions and coming up with signal space coordinates is you've got the coefficients, and each point in the space is a coordinate, or with the coordinate axes being the basis function. So you abstract what is going on, and I think I have a picture in here. So this is a picture of a 3-dimensional expansion, but it's just saying that phi1, phi2 are in the plane, horizontal plane, and then phi3 is in the vertical plane, and you're getting the coefficients along those 3 axes. The projections of the signal vector are those coordinates a sub I1, a sub I2, a sub I3. And then if you need to represent noise, the noise is going to occupy the same use the same 3 basis vectors. The signal will have exactly those 3 dimensions that are needed to describe it. The noise, being that it's white noise, it has an infinite number of dimensions, but the dimensions that aren't used to represent the signal are irrelevant. Just like when we were doing BPSK, we had the signal points at -1 and +1. Complex noise could be here, horizontal, in phase, and then quadrature. But any noise that was showing up on the quadrature axes would push the signal plus noise off the real axes. But when we're going to do a decision, we're just going to look at how it projects onto the real axes. Right. So this is just looking at that picture. That's a noise cloud in 3 dimensions, and it's irrelevant. And those are things in the detection theory class, part of 5615, or the specialized class, that get talked about as well. So when we go into the signal space idea, it's the constellation points that really matter to us. and those are used in the expansion of the waveforms that you choose for your signaling scheme. So if you have waveforms you're choosing, then you get their coordinates by projecting that waveform onto the bases functions, and then you will have those individual coordinates. Likewise, you can project the noise into its components as well. So the system that does that for us is a correlator bank, and we talked about this in the last chapter when we were talking about an alternate way of looking at a matched filter. A matched filter was the time reversed impulse response. The correlator was multiplying the received signal by its same waveform less the noise, and then multiplying the two together and then doing the integration to complete the correlation. Now when you've got your signal represented in the bases functions, you don't have a single signal that you correlate with. You have all the functions that form the basis set that you correlate with. And noise is included in the y, so y of t is signal plus noise. And then you get the projections effectively. That's what this correlation operation is doing, because it's carrying out that inner product, right, that we showed with the integral. It's carrying out that inner product. These would be conjugated if they're complex basis functions. And then the z1s are the projections of the received signal onto those basis functions, along with the component of the signal itself plus the component due to the noise, which is going to be a random variable. So these are the outputs, and the aij's would be deterministic since they correspond to the signal set design, and then the nj's are the random variables. And they have zero mean and some variance corresponding to the n0 value, and then through the basis function. So the way we've got it, since it is white noise, it turns out to be n0 over 2. The most important thing in all of this is here, signal space representation preserves the information needed to make the decisions on what signal was transmitted. If we were to do some technique like this and that was not true, no one would want to use it, right?
Yeah.
Because then they say this is not optimum. I can't start with a non-optimum solution.
I guess, can I restate this simply? I guess sine and cosine, for example, are orthogonal,
Right.
So you could correlate with sine and correlate with cosine to figure out how much energy the transmitter had in each one.
Mm-hmm.
And then you could, for example, I guess have a signal that's like 0 sine, 1 cosine, or 1/2 sine, 1/2 cosine, and
Yeah.
you can make arbitrary signals from phi1 and phi2, right?
Exactly. That's exactly what we're going to go do. So you've got it exactly. The one thing that I'll comment, you said the energy is true in making the decision, but when you do a correlation, there's a sign associated with it too. So if it was BPSK, it would be whether it was a positive correlation or a negative correlation.
Sure.
But the absolute value of that is related to the energy. So.
But then in that case, I guess we'd have two. We just have phi1 and phi2, but we could make arbitrary combinations of them to make a variety of S, right?
Variety of signal points.
Yeah. I mean, we can make as many as we want as long as we don't care about noise, perhaps.
Yeah, well, there's actually some problems that'll be coming up. It's either the homework or the final exam. I've got an interesting constellation that gets looked at usually as a final problem that is got a name that somebody gave it, but I have you do the analysis on it, and then the optimal decision boundaries, which come about from this analysis here, are more complex than a simplification, and then I have you compare the two of them and see that it doesn't hardly make a difference. But it's interesting because it was created for a reason. I'm trying to remember what the name of the modulation is. I haven't looked at it for about 2 years, but it's just an interesting exercise to be able to go through it. So here's back to this picture. I don't think there's anything more I need to say, but this gives you, for me at least, and hopefully for you, and engineers I think like visualizing things. If that's not true, then I don't know why I've survived so long in engineering, because I like visualizing things, but so we like having pictures. And this just gives you a mental view that I project this signal onto these 3 coordinates, and then I get a signal space, and then I can look at what happens if I have a second point in the signal space, and that, you know, that ends up being exactly the case. So it ends up being that we'll have another point that will be sitting over here, and it has its noise cloud all around it. And what our receiver ends up doing is it ends up, it's supposed to be a straight line, but it ends up drawing a line like that in the n-dimensional space, or m-dimensional space, and then if they're equally likely, there's a perpendicular bisector, and that forms the decision boundary between one side. You'll classify it or make the decision that it was that type of symbol, the other side it was the other. If we have m different or k different types of symbols, then it gets more complicated, and we'll see how that works out though, because there are some other cases coming along. This is how it factors into the general detection theory problem though from the other class. So we don't really have as much of that here, but it'll come into this one problem I'm thinking of from the final. This is also something that I like a lot, and data science people that are doing hypothesis problems, decision-making problems. I think we have I don't know, I like the approach that electrical engineers developed. I think data science people have taken it over to some extent, but they don't use all the same names. They use some of the names though. Okay, so following the correlator bank, the decision is based on the minimum squared Euclidean distance. So I was just looking at that in the picture up above there. The Euclidean distance is the distance between a point, like if a signal comes in and you get a point right up in here, you're going to get the Euclidean distance between here, and then this is another, not drawing this really well, that's another signal point there. And then you square that, and that's the official squared Euclidean distance, and the signal point that the received signal is, so this is R for received. You classify or make your decision based on the minimum squared Euclidean distance. But then if there's irrelevant stuff in between, then it turns into that perpendicular bisector if they're equally likely and things like that. But this is formally the rule, and then it can be simplified. This is the rule for equally likely though. So if we go to QPSK, this is exactly what you were saying, Joseph. We'll expand in basis functions, which are sine and cosine, and the square root of 2 over TS is thrown in there because that ensures that when you integrate this, so that would be called the norm squared idea, which is the 2 double brackets or double bars on each side. That becomes the integral of integral of the basis function magnitude squared, and the normalization is such that it's 1. So just like in linear algebra, you'd make your basis vectors have a unit length. So that's just why that's thrown on the front of that. And then once you do the expansion, then you can write for the QPSK case, you can say that a given QPSK symbol is transmitted as plus and minus phi1 plus and minus phi2, and then the square root of ES over square root of 2 is thrown up inside of there as a scale factor on the signal points. And then in signal space, you just extract out what the coordinates are. You don't need the functions anymore, so this notation is just simply to say that's the projection onto the phi1 of t function, and the vertical axis is the projection onto the phi2 of t function.
Right.
Is that good?
Yeah.
Okay.
And I guess if we wanted to, we could add signals of like square root 2 phi1 and minus square root 2 phi1. If we wanted to get 8, right, those would be the logical places to put them.
Yeah.
We could put points on the phi1 axis and phi2 axis.
Yeah, well, that'll be M-Mary PSK. All the different angles are used, and then QAM.
But
And then,
still the same two basis functions.
exactly.
Yeah. Okay, that makes
Yeah. There's only, really, this is the most popular scheme, is to use just these two basis functions, but there are other uses of signal space ideas, and that would be in generalized phase shift keying too, and we'll see that where we'll use a possibility of an infinite number of dimensions for M-Mary FSK, but we haven't gotten quite there. This is pretty much where we're at, though, in our stuff. I mean, I was studying OFDM from Friday on and off over the weekend, and orthogonal frequency division multiplexing. OFDM is used in LTE, and it's used in 5G, and so on. It has all of these subcarriers, and then you use the inverse FFT to go from the frequency domain to the time domain, then upsample it and transmit it on a carrier, and then downsample it, decimate, and then you go through an inverse FFT to get back to, or FFT to get to the frequency domain. And we're going to be seeing this, but each of the frequency domain points in the FFT are actually a complex signal that is this signal space right here. It's just, there's many of them, many subcarriers, but each subcarrier will have a basis set like this of the real and imaginary parts based on sine and cosine underneath the whole thing. It's pretty cool. The guy that invented it, I won't go down that path. I want to talk about it because it's pretty exciting. You will have an interesting problem to work with it, though, and a simulation problem that you'll be working with in the final project with OFDM. So you get a chance to play with it, and it's built into the digital comm module. Some functions are, as are all these others. So the decision boundaries I think are denoted in here. The way this is shown for QPSK, it's rotated so that the decision points are at 45, 135, 225, and 315 degrees, or minus 45 degrees. So it's kind of a tradition to do it that way for QPSK, but understand that you could rotate this whole constellation by just 45 degrees, and then two of them would be on the real axis and two would be on the vertical. But this idea here makes it break out so that the decision region, that's the S1 decision region, and then S2 decision region is, and so on all the way around.
By any arbitrary angle we wanted for fun.
Yeah, and actually see it's spinning when it comes at you because of the epoch. You don't know the carrier frequency as the signal hits you.
Or if there's jitter, it'll rotate.
Yeah, it'll be, and we'll see that in the code that I'll be running in the Jupyter Notebook. So the minimum distance decision rule reduces down to these quadrants. In other words, if we had a point, if the received point is right in here, because of some noise, there's a noise cloud, and I guess, yeah, so there's a noise cloud, then you would go ahead and say, what is the minimum Euclidean distance? So you're measuring distances between here and you're going to make your decision based on the smallest Euclidean distance, and it would be S1, obviously. This also, in thinking back to my meeting on Friday and thinking about Keysight and just digital comm measurements in general, one of the measurements that's always taken in a complex signal constellation like this is error vector magnitude, which is how much error there is in the signal points in a noise-free channel, and that's just due to other impairments in the channel, right? Little distortion impacts. So that would be saying there's a little cloud or a little error pattern around S1, even without noise, pushing it away from its location, and that's important, right? I mean, I know.
So like making those heat maps around each one, right?
Yeah, if you want to do it as a heat map, but right. So the slicing and all that kind of stuff can be looked at in different ways, but it reduces down to those quadrants for your decision. So all these bullets kind of take you through different things. I just looked at this as a picture. When noise is present, the signal vector is moved away from S1 by the noise vector having its components N1 and N2. And so the error probability will get altered, because when we go ahead and solve for the error probability, we're going to be looking for the probability that Z is an element of region 1 or region 2 or region 4, given that S1 is sent. So what did I just say by doing that? I just said that if we're looking for it to be, oops. Just going to clear all this stuff out. So if we're sending S1, the probability of error is that the received signal, Z, lands in quadrant 2, 3, or 4, right? So what is used in some scenarios, and that's pointed out right here, when we do this approximation, we're doing what's called the union bound. So we're overbounding the probability of error. And what this is doing, what this union bound is doing, I've got the words there, but I'm just going to draw you the picture. The union bound would just simply say it would be that half plane, and then we would have the half plane below. So we'd be finding out what's the probability that it lies, the real part, or the phi1 component is less than 0. And then that would be that green hashed region. It's everything in the left half plane. And then the other component would be what's the probability that the component along the phi2 axis is negative, and that would be the red hashing. So the union bound just says we're just going to add those two probabilities together, and we're going to ignore the fact that we're double counting in that quadrant 3, because that's what we're doing, right? So that's what, but the union bound is a lot easier to calculate. You don't have to integrate in 2 dimensions. You just have a one-dimensional thing.
Like the region of R3 would be the least likely.
That's right. And that also is in the gray coding idea. If we're going to gray code the symbols, our nearest neighbors are going to be quadrant 2 and quadrant 4, whereas the one that's furthest away and not gray coded is the one in quadrant 3. So I just walked through that. The union bound is going to be brought up as a modeling technique a little bit later for other modulation schemes. So if you're going with the quadrants or the half planes, you're basically wanting to find out the probability that the perpendicular component is less than 0, and that's landing in that, left half plane or bottom half plane. And that calculation works out by just integrating, say, from -infinity to the decision point. Let's see. This is through a change of variables, so that's why it goes up to minus square root of ES over 2. And that becomes just a Q function. So it's pretty easy to get that calculation. So now we'll advance this to M-Mary phase shift keying, and it'll be exactly what you said. And the very last homework problem in set number 5 is just to draw a picture of the decision regions for, I think it's 8 or 16 PSK. Not a real hard thing to do, but it lets you draw it out and say what are the decision regions. They're pieces of a pie, and it's pretty sensible stuff. So here's the M-Mary case. I runs from 1 to m, and m is generally a power of 2, so we'll go 2, 4, 8, 16, 32, 64, and so on. So the basis functions are the sine and the cosine again, and then the coordinates that land on those basis functions are cosine and sine of whichever angle we have, which is controlled by the symbol type. The m different symbol types. And then you get this for the signal space. Now, I don't know about you, but this is just how I always think about these types of modulations. I don't think about the waveform. I just think about what does it look like in signal space. And then when I finally get down to the end of the demodulator, I think, okay, I'm going to have to be coherent so that I can stop the constellation from spinning. And then I have to assume that the sample values I'm putting in the signal space model for the receiver have come about because I'm correlating, and I have the correlation integration interval, which is the timing parameter, set properly. So just like the homework problem you had where you had a skew in the timing, remember that one where you got part of the previous one or the next one, you've got it lined up, and that's the nature of the symbol timing. So you get all the energy for a given symbol collected up, and then it's the most information that you can, or it's all the information that you need to put back in your signal space. And then you have this side of the picture is how you visualize making your decision then based on landing in that piece of the pie.
So for PEM, just to make sure maybe I'm understanding this correctly, for PEM there's really only one basis function.
Exactly.
It's really just splitting a line segment up.
Yep.
And I guess the advantage is that should be simpler to demodulate.
Yeah, because you can do it. No. Coherently is still the best way to do it, but you can do different things. Well, you can't really do it non-coherently because you need to know the sign of the value too. You can't just put an energy detector out there and say, what did I collect? Because antipodal is the most efficient, whereas...
But there's only really one rotation to make, whereas here this has like...
whatever
symmetry.
Yeah, so it has m possible ambiguity points.
Whereas the PEM would only have one ambiguity.
Yeah. I think the pan that you're talking about is antipodal, right?
Yeah.
Because it's just way too inefficient to transmit energy higher and higher.
Yeah. It is antipodal. It's antipodal baseband.
Yeah. Okay.
That makes sense.
Yeah, all this stuff makes really good sense.
So then in our case, so in the case I'm looking at, V of t is 1,
Yeah.
and then it's antipodal.
Which is why over here, when I was creating this thing up here in the code, I just arbitrarily said, okay, I'll start off with this, because that is just a simple normalization. You would scale that up or down in amplitude depending upon the AGC or however the system functions. But the reason why 3, 1, minus 1, minus 3 is chosen, it's got to be an odd integer because you're not using 0 is going to be at the center, right? And then those values put the separation of 1 or 2 units between each one. 1 and minus 1 are 2 units apart. 3 and 1 are 2 units apart, and so on. So they're all spaced in that minimum. They all have the same minimum spacing between the nearest neighbors, which is not what happens in. Well, it's what happens in this guy too. This one doesn't happen in the real or the phi1 and phi2 components. It happens in the angular sense. The angle spacing in all of these is 2 pi over m. There's m different angles, and then the spacing between them is 2 pi over m. So
it seems like for these M-area PSKs, synchronization is harder because you have more ambiguities.
yeah, ambiguity is
More distance in signal space if you can synchronize.
yeah. But this is very efficient in one sense that makes it just wonderful in the fact that when you're doing phase shift keying like this, M-area phase shift keying, the constellation or the envelope of the signal is constant. It does not change. And that is a huge thing. In the other schemes, it does change. And QAM we'll look at next. And then again, thinking back to OFDM, it has a non-constant envelope also, which those non-constant envelopes are just a pain for battery-operated devices because you want to make the most efficient application means possible, but how do you do that when you have to have a certain amount of dynamic range? You just can't get away with it. Whereas PSK was invented during the satellite era starting in the 60s, where they said we'll just put up more angles and we can put more bits per symbol up. Log base 2 of m is the number of bits that's carried by the scheme. So BPSK is 1, QPSK is 2, 8PSK is 3, and so on.
Yeah, that makes. Right, and I imagine your radius can be smaller than with M-area pan.
Yeah, that we have to look at the model for and see how it works out. So we're going to look at the error probability calculation right now. So the error probability calculation, we see the decision boundary. The pi wedge is 2 pi over m, but then the deviation onto each side is pi over m. And that's what I've got noted right here in the picture, pi over m. And how do you get a handle on this? And that's what I have to walk through. There's an approximation, and then there's an exact calculation. So there's a simple bound. It's going to be based on the union bound. And then more recently, somebody's published an exact calculation, which is not too hard to go after with numerical integration. It requires numerical integration, but it's not something that's hard to integrate and has a problem converging. But the bound is pretty accurate, except at really low ES over N0 values where it's very noisy. Then it starts to deviate. The bound is not as tight under those scenarios, but remember the waterfall curve is very steep slope, so down in the steeper parts the bound is virtually exact. I think there's probably a homework problem that looks at that, or maybe I just have a picture coming up here. Probably have a picture coming up. Yeah, here's the picture. 8, 16, and 32. I can't even see a difference for anything. It's just exact. It's that close. The deviation is going to occur way back over here, which is at negative ES over N0 and dB values. I guess that's right. I've forgotten how good it is. So the way this approximation comes into being is the shortest point from the nominal signal point to the decision boundary is this perpendicular distance. So I've tried to draw that in here as that D value. And the reason why we're going to do that is we're going to use this triangle shape to look at the error probability. We're going to have a Gaussian PDF, and then we can effectively do that calculation using this zero crossing, or we're going to be looking at, try to draw this picture so it makes sense. If the point that we have is, say, right here, oops, I didn't get the right color, I wanted to go with green. If it moves like that, or moves like that, in other words, if it's moving due to noise parallel to the decision boundary, that's not impacting the error probability, right? It's only if it moves perpendicular. Right. And if it crosses. So if it crosses, that's what we care about. So that's the assumption that's made in here. And it's a symmetrical Gaussian PDF because of the white noise. So the error probability will be the probability, or the error probability is going to be overbounded by the probability that Z lies in either D1 or D2, and D1 is the upper region and D2 is the lower region. But then we have this double counting in here. So we have what lies above the line or what lies below this line. So we have two lines in here, though. We have this one, and then we have the one that extends like that. So we're going to double count that darker shaded region, just like that union bound example I talked about earlier. But they're the same probability, so it's 2. And that shortest distance is that perpendicular line running from the signal point to the decision boundary, and that ends up being, from geometry, square root of ES times the sine of pi over m. So if you model that with the circularly symmetric Gaussian PDF having its variance in each coordinate n0 over 2, and that was the development from the beginning, right, where we showed that with white noise going through the expansion, each component gets n0 over 2 in the basis functions. So that gets applied, and then that sets up this integral, and then that's a Q function. So the thing is that this sine pi over m is carried now inside of the Q function. And a big thing to think about that I always get confused on is Q is always going to have some proportionality to distance d in its argument. So d is distance, whereas energy is related to distance squared divided by the n0. So I'll just call this d squared.
So you're calling this perpendicular distance d?
Well, in the picture up here it was called d, yes.
Right, yeah.
I'm just trying to explain why, I'm just going after something that I get confused on, and I have to kind of slap myself and say, no, that sign is outside the square root, and most of us in engineering, we think in terms of units, right? So we think, what is the argument of the Q function? It's going to be related to not the energy, but it's the square root of the energy, and that makes it being proportional to distance. So the Q function argument has a square root term inside of it, but that is just to get you a distance without the phase angle to get it converted to the perpendicular distance. So that sign sits outside the square root is all I'm really getting at. Don't be confused that it should be inside, because that would give you the wrong answer. It's not what we're looking for. So I have this drawn not quite correctly, but the whole thing is d squared, so it should be something like d prime times sine of pi over m. D prime would be the nominal distance before you scale it by into the perpendicular distance.
Right, so with this double counting, you get a very easy upper bound to calculate.
Yeah. And the exact expression, which is derived in the book, looks like this. It's this numerical integration. And this is not something you can easily see. This is a very nice expression that somebody developed, and Dr. Ziemer put it in the book. If we had to do it from scratch, what you'd have to do is, if you were just doing this without that development that somebody wrote up in a paper, you'd be going over here. You'd be saying, okay, I have a Gaussian PDF that's sitting in here, like that.
You'd have to make rings and see where it crossed each one.
Now, well, what you'd do is you'd have to integrate in that pi wedge there, that two-dimensional Gaussian PDF, and you'd probably rotate it down. You'd do a change of variables so that it would be on the real axes, let's say. And then you would use symmetry, and then you'd be integrating half that pi wedge, right? And then you'd double it and subtract it from 1.
Yeah.
It would be a two-dimensional integral, though, right?
Yeah, I can see approximately how that would look.
Yeah.
But I'm happy I don't have to do that.
Yeah, and that's exactly what I'm trying to make you see. But somebody did develop this result, though, and that's in this blue boxed equation, and it's just in one dimension, and it's not a particularly difficult function to integrate, but you really don't need it. You have this bound, and the bound is the 2q with sine pi over m inside of it. So here's the guy that wrote it, Craig. Dr. Ziemer he has a couple other papers. I don't know, I think of him as a great guy because I like this paper and a couple of his other papers. It's like he went after the really practical things that people care about, and he published it in the Milcom conference, which I used to go to a lot. It's not one of the bigger IEEE Communications Society conferences. It's the Military Communications Conference, but he was This paper has got other interesting things in it. I've used this paper myself to review stuff. So we already looked at this. I did not put the QPSK and BPSK on here, so we'd have to do that, but we could figure that out, that we know around 10.6 is where BPSK would be, and then QPSK, I don't have that number in my head. This would be symbol error probabilities though, so notice this is not bit error probabilities at this point. So we're not really comparing apples to apples if we're doing symbol error probabilities, because that's not what we deal in. We deal with bits, right? So we'd have to do the conversion. That's coming up here too. But if BPSK wasn't to the left of the higher order modulations, you'd say, I don't believe that, because by throwing more points in there, you're obviously going to degrade error probability, because now you're bringing things closer together for the same amount of noise, and you're going to pay a price for that. But each one of those points carries multiple bits of information. Okay, the next scheme is that is pretty exciting like this, is quadrature amplitude modulation. And with this scheme, you're going to use the same basis functions, except now we're going to use a rectangular shaped set of coordinates. So we're going to run plus and minus a, plus and minus 3a, and so on up to plus and minus square root of m. So when we have, say, 16 Airy QAM, quadrature amplitude modulation, we're going to have that upper limit there is going to be 4 for 16, so we're going to go plus minus a plus minus 3a, say for 16 QAM, and we do that in each coordinate. The square root is in there because of the fact that the points are going to lie along the phi1 axis and the phi2, and all of the points is what makes it the m level that it is. So m is equal to 16 means there's a total of 16 points. There's 4 different values that can lie in one axis and 4 in the other, and then when you square that, you get 16.
Can you scroll quickly? Sorry, I wanted to copy that formula.
Yeah, I just wanted to point that out because you have to think about that. This scheme is immensely popular today in cellular telephony. But as a signaling scheme, it's got non-constant envelope because of the fact that the constellation, just like 4PAM, 4PAM is like just the real axes only of what's going on. You're using amplitude to carry information, not just phase. And phase stands up better under nonlinearities than amplitude does. So this is the signal space, and now that we're seeing this versus versus M-Airy PSK, the signal space idea is what I always think about, because then when you do a scatter plot, you know, in a scatter plot that we talked about a while back in the previous chapter, we said, well, how are we going to measure performance? We can look at I-pattern plots, then we can look at scatter plots. The scatter plot is at the receiving end of a system, a very close representation to the signal space plot. You know, we're going to send 4 points or 16 points here. The pulse shape we're using, haven't defined that, but just abstractly we're saying we have 16 points. We're going to encode it with pulse shaping and carrier frequency, and then when we get it all the way out through the back end of the receiver, we can get a scatter plot after we made our calculations in the receiver, and then that is very similar to what our signal space plot looks like, except at the receive end, these points will not be sitting at those locations. They'll be deviated from those locations.
I guess you can measure how good they are by measuring the minimum distance between these points versus the minimum distance in QA and QPSK.
Yeah, for example. But this is more complicated calculation. PSK is very straightforward because each nearest neighbor is the same orientation to its nearest neighbor,
Right.
Whereas in QAM, there's, as this picture which comes from the book shows, type 1, Roman numeral 1, 2, and 3. So those are the different types of symbol positions that show up in the constellation, and their error probability calculations are all different. You've got the interior ones are bounded by a square box. The ones along the sides, top and bottom, are like a trough that goes out to infinity or minus infinity. And then the ones up in the corner go out to infinity in both directions. So the most constrained, the poorest performing symbol locations are the ones on the interior. The next best are the ones on the sides that have the trough. And then the best are the ones in the four corners, which don't have any competition in two directions. You see that?
Yeah. I was going to ask what those Roman numerals are.
Yeah, that's the book's notation. So when it comes down to what is the average energy sent in a QAM signal, this can be calculated. Maybe this is a homework problem too. I don't think I assigned it, but the energy, the average energy, so sometimes in the book he'll go like that, a bar over the top saying ES bar. The instantaneous energy per symbol is different, but the average energy is going to be plugged into here. So if you're using this formula, this is ES bar, and then A is related to the average energy. So that tells you how to scale your constellation in terms of M. So we have two correlators in the receiver, one to correlate with the cosine, one with the sine, and then you get the values coming out at the optimal decision instant, and then you have thresholding to do and decision logic to apply to get the symbol back again. The calculation of the symbol error probability is tedious, but it's not super long and difficult. Like I said, you're going to be doing this in, like I said, there's one new modulation scheme you'll see fresh for the final, and maybe there's something else between here and there, I don't remember, but you should just be able to do it because the pattern is the same that's been established either by PSK, that one's pretty much all wrapped up, but variations on this idea show up in other problems you might bump into. In other words, you will look at the constellation and you will say, what are the different types that I have to deal with? And then you'll just have to break it apart. And then to get the average probability bit error, we'll do exactly what we've got in here. I didn't give all the gory details in here, actually. This is the top level result. It just says probability of error is 1 minus 1 over m, and then a scaling factor based on how often that type 1 occurs. For 16 QAM, there's 4 of those. So that's what some of that scaling is that's going on inside of here.
Right.
So that's probability of being correct given a type 1. So this is
I see. So that square root business is saying how many of each type is there.
yeah. So for 16, that would be 4 minus 2 squared, which would be 4.
Right.
That's what you're saying.
Yeah, that makes sense.
And then there's a of the channels. I call them the channels. Why do I call them the channels? It's because these types, if you're actually setting up your integral, you're integrating over this channel which goes out to infinity. There's, so many of those, and for 16 QAM it looks like there's 2, 4, 6, 8 of those types. To try the other types, type 1 is just inside of there, and then the type 3 is goes off to infinity in 2 directions. So that's the type 2. And I guess if we looked at this, we are going to see 8, right? Because this will be 4 minus 2, which is 2, which is 8. So and then just, there's always 4 corners no matter what m is, because that's all there are, right? In 2 dimensions, 4 corners. So then you can go through the calculations. Probability of correct is going to be 1 minus the probability of being incorrect, and that's, you have to delve into that, and I'm not going to get super detailed about it. It is in the book though, and you do have to do this in the problem that I'll give you on the final exam. So the 1 minus 2 and then squaring it has to do with the independence. The squaring is due to independence. The probability of crossing the threshold vertically is independent from crossing the threshold horizontally, because the Gaussian PDF is circularly symmetric. So you get that independence. And then the 1 minus 2q, I can just give you the idea behind that. If you center the thresholds, no, 0 to a, is that right? Look at my picture. Yeah. If you center this value in here about 0, then you'll have minus a to plus a. So what you're doing is, there's 2 tails that are the error probability. So that is this 2, and that's the probability of being in one tail. So 1 minus that error probability is then the probability of being correct, which is being inside. That makes sense?
Yeah.
And then the squaring, like I said, is because you've got this on the vertical and the horizontal, and they're independent. So that's how you'd get that. The type 2 is the channel scenario. So the channel scenario has a bounding just up above and below it, or just to its left and right. So you're going to get the 2, and you just get one of those terms, and then the other Q function term is the open channel, the channel that goes out to infinity. So that is, there's just a 1 in there, because there's no chance of making an error on the side that goes out to infinity, because there's nothing to get confused with it. So that's how that term gets formed. Then it's the product of those 2 types, again using the independence of the noise in each coordinate. And then the corners are going off to infinity, so that's why this is 1. And you've got 2 of them due to symmetry in each of the coordinates, so you get the square. So that's where that comes from.
That makes sense.
So all of the Q functions end up being of the same general form when you make substitutions. They all look at the same form. I mean, why is this so nice? It's because of the regularity of the constellation. I mean, I didn't point this out, but all of these have the exact same Q function argument.
Right.
And then if you want to write it in terms of ES, and this should be like ES bar actually, then that's the approximate formula. And what is going on in here is ignoring any term that involves Q squared is going to get dropped, because it's going to be asymptotically as you move down the waterfall curve. If your error probability is like 0.0 is like 10 to the minus 3, the squared Q function term is going to be 10 to the minus 6. So that's much, much smaller and allows you to simplify things. So I did a formula compare on that in Mathematica. And here you do see some deviation when you get down to the low SNR values.
Right.
But other than that, they're pretty much right on.
And that area looks about the same as for QPSK, or no?
This is ES over N0 again. I don't know. I think I have them plotted on top of each other here eventually. I don't have them right here though. Another thing to notice about QAM, and I guess it's MPSK too, is that really low SNR. It's not like with a binary scheme you end up in a coin flip where if you just make a random choice, half the time you're correct. So your error probability is 1 minus that, or 1/2. But when you have an M-ary scheme, then you're much worse just guessing, because your chances of being incorrect are much higher, and that's the 1 minus 1 over m. So whenever I'm doing error probability curves, first off, you see something like that and you say, no, error probability can't be greater than 1. But that's because of the bounding. So that can happen. And then what you do want to see, though, like from the exact expressions, that somewhere far to the left, it is going to that 1 minus 1 over m value. It's not going to go to 1/2. So if you're, again, for me, I just look at certain things as like, is this even right? Let me check this endpoint value. I mean, just check sort of the corners of things. I think engineers do that, right? And we just sort of look as a quick check, is this making sense? And I've been thrown off by that. I forget, it's not going to do that if I'm plotting symbol error probabilities. So we have a couple more to do, and then we'll be on to some other stuff. So I guess I'll take a break right now. It's 9:30, so we'll pause and go walking around a little bit. Okay, we're back from our short break. I was getting things up and running in Jupyter. I'm going to have to do a pull request with my co-author and found a little bug. It's way buried deep in the synchronization module, which is definitely not our main theme, but I wanted to show some synchronization stuff maybe today. But the Jupyter Notebook itself has got a few more bugs in it too, just because of the way the function naming conventions were modified. So I will push that up there when I get a chance to settle down, and it'll be the most recent version. So the next modulation scheme is FSK. This is coherent FSK. So you just have the number of basis functions and the m level are in one-to-one correspondence. So you have a different basis function for every symbol type in Emery FSK. And this is defined here by just defining a frequency shift onto the base frequency FC. So you're going to move it multiples of delta F controlled by the index I. So when I is equal to 0 or I is equal to 1, it's at FC, and then you just move up higher in frequency. The signals can be theoretically made mutually orthogonal if the increment of delta F is 1 over 2 times TS. And you can prove that by just taking a cosine at a frequency FC and correlating it or multiplying it in the inner product definition times the frequency at FC plus this delta F. And then you'll see that when you go through the trig identities, you'll have a sum and difference frequency, right? When you multiply cosine at F1 times F2, you'll get a sum and a difference. And because those sum and difference frequencies have this delta F being 1 over 2 TS, and you're integrating over TS seconds, that makes it go to 0. But as a matter of practice, and we saw this in binary FSK, as long as FC is very, very large, when you do the integration, you get a constant in the denominator, which is related to the absolute frequency. And when that's large, it doesn't matter what the numerator sign in, terms are, whether they're 0 or not. If they're bounded by 1 because they're the cosine of something or sine of something, as long as that term in the denominator is very large, it still is very tiny.
Right.
So you can do it that way too. So that's why I've got it as long as delta FTS becomes large. So this is Dr. Ziemer's rendition of what the signal space looks like. Each coordinate axis there has got a signal on it, S1, S2, and S3. And then you've got the shading that he puts in there are the slicing up into planes, your decision planes, where you would decide, depending upon which of the 3 regions you lie in, which symbol you decide if it lands in that region. But you can do it by another means. You don't have to think about locating it in a 3-dimensional space. You can just project it down and again use the minimum Euclidean distance.
In theory, you could mix them, right? Like you could do V1 plus V2 and so on.
I don't know. I've never thought about that. I mean, use sums and differences of the basis functions.
Right. Yeah. I mean, I imagine it should be possible, right? Even if it isn't typical.
You can do, you can create your own modulation, is what you're saying, I think. Let's try something and see what this does. It'll be suboptimal in some way, but unless you've got perfect orthogonality. Actually, we know orthogonality doesn't do us the best. We learned way back when we were looking at PSK, binary PSK, and coherent binary FSK, that orthogonal is not as good as antipodal. Remember that? So, and people have studied that a lot. But in the case of FSK, orthogonal is the most common. There was a homework problem where you were looking at finding a frequency that's not an orthogonal frequency, but actually has a negative correlation. So that actually made the distance bigger. The signals are in the signal space would be a little bit further apart if the frequencies are closer together in 2 dimensions, but I don't know how that works out for 3. I've never really seen the analysis. I'm willing to bet somebody's done that, though. He just said, if I make them a little bit closer, what does my decision space look like, and what's the performance I'm going to get? But for the binary case, for the Emery case, where the frequencies are assumed orthogonal, this is what it comes down to. You're just looking at a decision boundary between any two frequencies is going to look like this, and the two closest frequencies, there's going to be a decision boundary between them, and that's how we can get the error probability calculation from this idea that we're getting the minimum Euclidean distance, so the error probability is controlled by that distance at the perpendicular bisector. And then this integral turns it into a Q function, and then we go ahead and this is for any pair of frequencies, but then you consider the union bound like we used before, and you're going to overbound it, and you get the m-1 out in front of it. And unlike in antipodal signaling, we've seen the 2 ES in there. We don't have that for the case of orthogonal. That's the 3D penalty we saw for the binary case. And then it gets worse by the m-1 for the M-ary case. So I did this in Python too, but I have it pictured here in MATLAB. This is what the spectrum looks like for M-ary FSK. I drew this picture out just because I'll show you the other results for the other schemes, but this is showing you what happens if you set delta F equal to that orthogonalizing value. That's the red plot, and we make it tighter than, no, it is, never mind. The tight one in there is the delta F is equal to 1 over 2 TS. Oops, trying to draw on this. So the minimum orthogonal spacing is the blue one, because this is just rearranging the math there so that you put RS in the denominator. There's something wrong with that, though. Doesn't look right to me. I have this written wrong, I believe.
I don't know, that seems reasonable.
No, but the units are not right. This would be delta F times TS is equal to 1/2. So this should be that. Should be delta F over RS. What was bothering me is that I had frequency times frequency, and that can't be equal. It's got to be frequency divided by frequency, or frequency times time. So it's a time bandwidth product. So if it's 1/2, then it's minimum orthogonal spacing, and then if it's 2, it's 4 times that. The red one, though, is more makes more sense if you want to use a non-coherent receiver, because you would just place bandpass filters or use an FFT if you want to think of it that way. You could think of using an FFT to FFT the signal and then see which bin the energy is largest, and that's how you could decide which frequency was being sent. Does that sound reasonable?
Yeah.
But the bandwidth here is huge then. You're going to be using...
I also imagine, and I don't know if people actually do this, so I guess I'm curious, would it be reasonable to, you're in the complex space anyway, so couldn't you kind of take the derivative of the instantaneous phase because you have a complex signal? And
Yeah, exactly. That'd be a discriminator.
right.
The discriminator type to get the... then you get an M-level signal back again, and then you can threshold it. You're right. You're absolutely right. Phase lock loop can do that too if it tracks the instantaneous frequency with a wide enough bandwidth. So yeah, there's a lot of different things. The discriminator is more old-fashioned, traditional way of doing it. It's the derivative. It's approximating the derivative of what comes out of what the received signal's argument is. So since we're looking at this, we have the non-coherent FSK, Emery FSK, same transmitted signal, but then you're going to use the wider spacing like I was talking about, and these are equivalent to bandpass filters because these are correlators using the individual frequencies, and then this is very similar to the idea of taking the magnitude squared of the FFT bin that you would process it with, because that's very similar to what the FFT would be doing, each of the bins, and then you would integrate the energy, and then take the magnitude squared and then compare it to a threshold. The one that's the largest is the one that was sent. I don't have the proof of this, it's in the book though, but for Emery FSK, non-coherent FSK, this is what the result works out to. It's a pretty long calculation in the book. It's interesting, all right. From my interest in modulation theory, I've just used this equation, I think, and something that I did a long time ago for frequency hop spread spectrum is probably where I was using this Emery FSK result. I mean, honestly, the way modulation theory goes, if you're working at a much higher level in the development and you're not wanting to understand individual impairments on each scheme, you're just wanting to have a catalog, you'll see in textbooks where they'll summarize everything by just having a collection of formulas for all the different Emery schemes, and then you can just simply pick one or just understand that this one's being used for this scheme, like OFDM is using quadrature amplitude modulation, and it's using the coherent formulas, and frequency hop spread spectrum would use some equations from this non-coherent Emery FSK perhaps. Okay, a couple more things, and I'm going to look at something in Jupiter. Jumping back to PSK, and then back in the previous chapter, we talked about differential PSK, and that was where we could send, we wouldn't have to recover the carrier, we would just make our decision based on the change in carrier phase, and that was intimately related to the idea of differential encoding and decoding, which is something you can do independent of the modulation. You can always differentially encode and decode outside of the modulation chain, and then you can use that to resolve ambiguities, and that's what it's used for at times. But when you roll it up inside of PSK, you can take out the needs for the coherent carrier because you can use a differentially coherent demodulator, which doesn't require an actual carrier phase tracking system. So going back to the MPSK that we were looking at before, this would be just looking at Emery differential PSK, and this is just a model that was put together to say this is what you're going to transmit in the first interval, and then in the second interval you're going to transmit just the differential phase. And so these two forms, or these two signals, would be used to try to figure out how I can make a decision without tracking this value. Just use this as a model to see what changes, and without knowing FC or having to assume it, then you can discern which of the phases you're on in the second interval. And did I put the footnote on here? Nope. It's on page 503 of the book that differential MPSK has a formula very similar to what the Craig formula was earlier, and I think he's the one that did it. I'd have to look in the book again to make sure. But it was either him or somebody else that wrote another paper after reading his paper. Just make sure I remember that. Look on page 503. Now, it is Pawula, Pawula, in 1998. A new formula for M-ary DPSK simple error probability. I was already teaching here when that came out, but Dr. Ziemer, again, was very excited about it, so he added it to the book. And I just put it in my notes because, you know, it seems interesting. But, you know, certain modulation schemes are mainstream, and then others are just sort of off to the side. They find certain applications, and they may get put in a new scheme, or they may not. The mainstream ones, though, are following the pathway of, you know, in cellular, first, second, third, fourth generation cellular, just like the PAM, I guess, in the PCIe bus. I mean, what makes something popular? I don't know exactly, but it has to have certain good properties that people have liked, that they want to move the next generation of the device development into that same scheme. But I guess in the
good properties and well understood literature.
Yeah, that's what I was going to say. Good properties, but also well understood. People don't like, I think, in communities where you're selling things to make a living, they don't like making a major shift like a hard right turn or left turn and saying, we're going to go off and do this now, and then try to convince the community we should do this, and they better have really good reason. I mean, the thing that I worked on, I've talked about before with the space-time coding for telemetry links and test ranges. They had standard techniques in the families we've already been studying, and then they went off and decided, a guy at Brigham Young University, Michael Rice, decided with some of his friends at a company that he's been associated with that they should switch to this CPM, which was similar to my thesis, and then do that with space-time coding. It added tremendous complexity, like many Vertex parts back when it was first developed had to be in the receiver, and the receiver would be in the ground station, so that wasn't a factor in the box that had to fly. The transmitter is not nearly as complicated, and I mean, there's all types of conditions, but how did they decide to make this big jump? I don't know. I mean, I worked for the company and helped them on the receiver, a simplified receiver, because they needed to add that to their suite of schemes to stay current with the newer standard. I mean, they had to have a box that they could sell somebody that, yeah, if this aircraft is going to fly with this new telemetry scheme, we can demodulate it. We can get the data back. The performance of their link might not be as good as what the designers intended, and their product might do slightly better, but that's again another thing that people get into, right? My box will do 4 of these schemes very, very well. The newest scheme 5, we don't have the same exact performance, but we don't find that people are demanding that much right now, so we'll be working on that, improving it, but no panic. I mean, that's the other thing about industry standards. I mean, we have to have backwards compatibility, so USB 2 to USB 3, that's lingered on and on and on. So why did they do that, though? I don't know. I can ramble on it like I'm rambling because my dissertation was on multi-H CPM, and I left being interested in it because although it had really elegant math, nice performance, it was terrifically complex to synchronize and build the Viteri algorithms for doing the maximum likelihood sequence estimation. And I just said, enough is enough. I want to go do something else where I can actually see something get realized. I just didn't want to continue to work on something that seems so far off the deep end.
And I guess that's an interesting trade-off that you mentioned is you can, in some algorithms, you can have a simple transmitter but complex receiver or vice versa.
Yeah, usually the receiver is complex, and if it's ground station, no big deal. It sits in a rack and it plugs in, and
What you care about, I guess, is the satellite receiver because it has to run on a battery.
yeah,
But yeah, on Earth, you can have a complex receiver if you need to.
But see, a cellular telephony, not so, because you have base stations that can have many antenna arrays. That's possible in many receiver architectures, but on the handset, you just can't put lots of antennas or have a lot of receivers running in parallel necessarily because of the battery limitations.
Right.
I don't know, I think we're the engineers, so we get to do the fun stuff. We get to play games. The consumers just get taken for a ride all the time. And if they like it, we make money, or the company makes money. If they don't like it, it may go out of vogue pretty quickly. And that's certainly what we've seen. But we get to have fun when it's being developed. Okay, the next little investigation here is just to take care of something that will come up, we'll see in practice. Bit error probability from symbol error probability. So when comparing modulation schemes, we generally want to put on an apples to apples comparison, and that would be the bit error probability. In that, when we go with the Emery schemes, we generally go with gray coding or gray encoding so that adjacent symbols in the symbol space differ by only 1 bit. And when that is true, then we can approximate the bit error probability as a lower bound of the symbol error probability divided by what you see down here, log base 2 of m. So what you're saying, this is kind of crude, and you're saying, but, that's not going to hold under all conditions. But when you're way down on the error probability curve, one symbol error generally leads to a single bit error because you're not going to get so close to other possible symbol locations that would carry more bits of error because of this gray coding. So we use that a lot. And then for orthogonal signaling, you can go with natural binary assignment made, say m is equal to 8. This is talked about in the book. I've never actually done this, so I'm always fuzzy when I have to try to explain it. But Emery signal, you can have representations that are convenient for the orthogonal signaling, just like we do in the two-dimensional signal spaces. This would be for the m-dimensional signal space. And then this is the result there. Probability of bit error given a symbol error is this ratio. I've actually never used these formulas though, but this is what that conversion factor then is. I'm just simply reporting what's in the book. So, and then the other thing is, for all the schemes, we have to take into account the change in symbol energy. So if we transmit ES symbols, or ES joules per symbol, then when we want to change our footing to be symbols to bits, we also have to change the horizontal axis to be energy per bit. And that's a conversion to go log base 2 of m times EB is ES. Or if you're going in the other direction, you're going to go and divide. So using that, so just to be clear, this is the that's how we take symbol errors to bit errors, by dividing by log base 2 of m, and then this ratio here gets shifted so that it's going to be ES over N0 minus, oops, I just felt inclined to write it that way because you always have less energy per bit than per symbol. So you have to just recognize the fact that you're going to always subtract. So ES over N0 was 10 dB. The equivalent energy per bit is going to be subtracting 10 log base 10 of that log base 2 of m value. Just make sure you're always going in the right direction so you know it's going to be smaller. So it moves the curve more to the left when you do that conversion. So here's MPSK, MQAM, and MDPSK formulas. I don't have the curves overlaying, and I guess I didn't remember that I did. I did write these out myself, though I didn't take them from the book. You'd have to look at the exact threshold values and see like where they cross, and you can do a quick comparison now by just looking at where these values are occurring, and so on, to see which is better. I think QAM, you can see, is just a little bit worse than MPSK. It's pushed out just a little bit further. A little better or a little bit worse? I guess. Oh yeah, that's right. I'm looking at the wrong curve. Yeah. Never mind. I was looking at the wrong set of curves. I put those red arrows on there for a reason, and now I didn't use them. So that's what the red arrows are there, is trying to compare similar curves. So the MQAM is the best. The MPSK is the next best, and then the differentially coherent MDPSK is the worst. It's over 30 dB at 10 to the minus 6th for m is equal to 64, and under 20 dB for MQAM, and then just under 30 dB for MPSK. But they all have different advantages. I mean, constant envelope is what MPSK does, but I think from systems I've worked on in space systems, generally people will use 8 PSK, but I generally don't see them go higher than that. And QAM starts at 16 and goes up, to 64 and 256, and even higher than that, 512, I think, is used in cable modems. And I don't know if OFDM that is used in telephony goes up to 512, but I know cable modems take and use QAM extensively, and they take it up really, really high. They're trying to pack as many bits per second per hertz of cable bandwidth so that you, the consumer, can pull down all your fun stuff, movies and streaming, this and that.
On a wire, you can assume better SNR than wireless, generally.
Generally, but the problem, and that's true in cable when you're pulling down, because it's pretty clean at that point, but when you're pushing up, you have an ingress problem. You have all the homes are feeding back up to the same head end, and there's a lot more ingress, which is why it's
easier to have a fast download than
yeah,
others.
because
It's interesting because I grew up in New York City and everyone offered symmetric up and down, and now I moved to the Springs and you're lucky. Here, like, people will give you as fast download speed as you want, but it's impossible to get a good upload speed here.
I think that's the infrastructure of the cable.
Yeah.
You must have been on something different in New York City.
Yeah. But I think it's more typical to have asymmetric up-down, but I think on the East Coast, the big cities have more symmetric up-down.
I didn't even know that was available.
Like
I
I
don't.
got 100 up and down for less than I'm paying here for 100 up and, or 100 down and 10 up here, I pay more than in New York I paid for 100 up down.
Okay. I can believe that though, because you go out into more rural areas and it's just
Yeah.
the infrastructure.
Economy of scale.
Yeah, exactly. I did have a student, a master's student, who for a while worked for a company that developed cable modems, and in the process of talking with him over the years when he worked for that company, realized that Cable Labs is actually in Denver. It's a company that's the standards body for
Oh.
cable TV boxes, and it's it's QAM and stuff like that. So I find it interesting that that's located in Denver. Why is it here? I don't know. It just ended up here. So go ahead.
Oh yeah, but I guess generally, I guess it makes sense that you get better SNR on a cable than wireless.
Mm-hmm. It's more predictable, but that's why the cable TV companies are so concerned about your integrity of your cable, how tight your joints are, whether it's leaking signal out or whether you have something that is allowing for ingress from some other appliance in your house or something that will get into the network and go upstream and then cause problems. Years ago we had the cable TV company. They drive around in their truck and they have their little dipole antenna, and they're looking for houses that are leaking a lot of energy out of the cable, and they don't give you a fine. They just simply say, you've got a problem, we need to fix that problem because it's the integrity of our network is at stake if we don't get you to get your connectors tighter. Or what they did for us is just said, these cables you're using aren't good enough, they need to be better quality coax connectors and made tighter so that they don't leak. Yeah. And that ties in with another aspect of cable. That cable contains a lot of spectrum that's regulated by the FCC for open air use, and one of them is like 113, 112 megahertz can radiate up off the cable, and that is used for aircraft talking to the tower. We don't want to be jamming a commercial aircraft that's coming in for a landing because our cable network is sort of wafting up all this garbage and interfering with their radios. So, and any other band that can interfere would not be a good thing. Actually, they signed up for the FCC to say our cable is going to not radiate, keep our radiation, spurious radiation down to some acceptable level, I'm sure. So if they don't do it, they'll get fined. So they have to manage that somehow or another. Okay, so this next little discussion is coherent FSK and non-coherent FSK. So these are some curves that appear in the book for plotting the equations that we have for the two non-coherent FSK and Emery coherent FSK are pretty similar, a little bit better with the coherent compared to the non-coherent, but the problem is that the bandwidth efficiency is going to be very poor for that one, the one that's non-coherent, because we've now spread the carrier signals out, carriers out further, and it's going to occupy a lot more spectrum. So the good news is, from the information theory standpoint, the power efficiency is really excellent with M-ary orthogonal. So the next discussion in here is getting into bandwidth efficiency. So anytime we've done error probability curves or done the bit error analysis, that's all been what's referred to as the power efficiency. And we care a lot about power efficiency in digital communications because we want to get by with the least amount of energy per bit. But that's only half the consideration. Well, that's one of the considerations. That's efficiency. Then there's efficiency in the build, of course, the hardware. In all schemes, we want to be as efficient as possible, but you spend more money and are less efficient if you can be more power efficient in the link. But then the thing that's also goes along with the power efficiency is the spectral efficiency. So start looking at bandwidth efficiency comparisons, and I think I come into that eventually. Well, I guess I'll go through this. I was going to jump over to Jupyter. I'll wait till I go through this. So if we just look at MPSK and MQAM, we'll see some equations here coming up pretty soon. They're not proven right now, but they're all, if we're using rectangular pulse shaping, they all have the same null-to-null bandwidth. It's 2 over the symbol period, or 2 times the symbol rate. And then if you convert that to serial bit rate, you can convert that through log base 2 of m times the symbol rate becomes the serial bit rate. So we have, this is the bandwidth efficiency of MPSK and MQAM, 2 times the serial bit rate, but divided by log base 2 of m. For coherent FSK, and this I think maybe was in a homework problem you did in the previous chapter, you have to consider the separations, and then you look at the approximations to the bandwidth occupied by FSK. You have the difference in frequencies between the 2 tones, and then you say when it's modulating on this tone, it has a spectrum that has side lobes on it, and at this tone it has side lobes. So you then take half of that side lobe spectrum bandwidth at the left end and half at the right end, and then add it to the difference between the 2 carrier frequencies, and that becomes your bandwidth. And when you plug that into the other equations with log base 2 of m to go in from symbol rate to bit rate, then you end up with this equation for the bandwidth of FSK. And this is for coherent FSK, where you're choosing this tight spacing. If you go with non-coherent FSK, you have to separate them so that the 2 spectrums are just touching, which means the center is going to be, it's the bit rate bandwidth to the first null, and then it's going to be 2 of those, so it's 2 over TS. So that changes the equation slightly, so you get a little bit bigger number for the same value of m. So you can put all those together.
So we saw that FSK has the best power efficiency, but the worst
Bandwidth efficiency. Yeah. It's simply pathetic in terms of bandwidth, but there can be scenarios where the bandwidth doesn't matter, like maybe deep space, where it's not congested out there and you're just going to use lots of bandwidth, but there still has to be a limitation, because if you have to bring it down to Earth, what's the footprint of that spectral information? It's like It's okay out in deep space, I don't care, but it's still got to reside in a congested region. So maybe you have a collector out further out, and then you convert it to something else to bring it down. I don't know. I'm not into deep space, but
Sure.
we're all into it because we pay taxes for NASA to go fly missions, right?
Yeah.
So we have the Mars rover. We have to look at what modulation schemes they're using. I haven't looked at it. Maybe I should abandon my typical assignments for this class and say go read about that and see why they chose what they chose for
That could be a fun side thing.
to go read about that.
Yeah.
It might be FSK though. I really don't know. Okay, so these are just some comparisons as M levels go up. QAM, bandwidth efficiencies just click at a regular interval because of the fact of the reduced, as the serial bit rate goes up, the bandwidth stays in check. So that's bits per second per hertz of bandwidth goes up, which is good. So higher is better. This is like MPG in a car. The more miles per gallon you get, the better you are in terms of using spectral resources. Coherent FSK goes down very rapidly. Non-coherent FSK is just pathetic, right? So this number at 64, this is 3 times bits per second per hertz of bandwidth. The other one is 0.05, so that ratio would be 100 and then 5 times that, so that'd be 20.
That'd be 60.
Yeah, 60. So 60 times worse. We're not going to let you send data at a very high rate if you're going to use non-coherent FSK because we've got to keep your bandwidth usage under control. So we're going to drop you by, your bit rate's going to have to drop by a factor of 20 or something like that. So the next thing is, that's the core basic, just with a crude approximation of null-to-null bandwidth. We can go now and spend more time studying actual spectral power spectra for these quadrature modulation schemes, and then we can deal more precisely with the bandwidth efficiency when pulse shaping is employed, worry about and measure that the FCC likes to use fractional autoband power, so you know how much power you're spilling over to your neighbor and stomping on them, which can be, you know, your cell phone neighbor. If you're both talking to the same base station, are you being assigned a different channel in the cellular network, and are you going to spill some energy into them? So the definition of fractional in-band power is just integrating the power spectral density for the given power spectrum, which is, you know, we're modeling the digital communications as a random process, so we get the autocorrelation function, get the power spectral density, and we normalize that by the total transmitted power. So that's the in-band power is going to be some fraction of the total power. Presumably it's a pretty large number, like 90% or higher, because it's not going to be, we don't want to give a lot of our power to our neighbor that's trying to transmit. So total power is integrating the power spectral density. So another measure that's used is the fractional out-of-band power, and that's just 1 minus the fractional in-band power, and that's the one that I'm most familiar with. It was actually a lot in my dissertation when I was looking at multi-H CPM, was how phenomenal it could do in terms of its fractional out-of-band power. It could be very, very tiny. And GMSK, we were looking at a couple weeks ago. GMSK has got that pulse shaping on that binary modulation scheme that made it be extremely compact. And that's what we use for Bluetooth. We use GFSK, but it's the same kind of pulse shaping. And GSM handsets, which was generation 2, used that scheme. So it was very good at fractional out-of-band power. I hear the class is starting to gather out there. We got 10 minutes. So this just compares some levels and figures of merit. It's common to use something like 10% or 1%. So when you integrate the power spectral density and then you take the complement of it, so you're getting the fractional out-of-band power, which is what this curve is plotting, you get these shaped curves. They start at 0 when the baseband bandwidth is 0. So there's all the power is, let's see, when you're at 0, baseband bandwidth over the bit rate is 0. So the out-of-band power is everything. And then as you increase the bandwidth, less power is going to fall outside of that bandwidth, and that's what we're interested in. When we get 1 bit rate away, then that is typically a measure where we might want to be 10% down or 1% down. And you can see that rectangular pulse shaping, which is what's assumed here.
Yeah, that's awful for that.
Yeah,
That's his sync, so it decays very slow.
yeah, exactly. So it's awful, like you said. QPSK is just simply shifted over because it's 2 bits per symbol, so it gets to operate at a lower symbol rate by 1/2, so that gives you an advantage. MSK, though, which has a main lobe that is wider, this is why my master's thesis advisor pushed MSK so hard. It rolls off a lot faster because it has that added shaping. It has that continuous phase nature. Linear phase trajectories make it smoother, which makes the bandwidth narrower.
That makes sense.
Okay, what do I want to do with this? Well, I want to go through that, but I want to look at something in Jupyter so you know what's out there to play with.
These fun raised cosine shapes.
Yep, and that's what I'm gonna look at right here. I think I've got it in here. I don't remember for a fact. So,
And you
yeah.
get 0 ISI. I guess the Gaussian has some ISI, right?
Yeah. Okay, MRAPSK, along the way, I just wanted to show you, since we've discussed it, what's available in the digital comm. That's the DC here. So if you look in what's inside of here, I've got an MPSK and an MQAM functions are in here. But then if you scroll down, I more recently added some more powerful functions. MPSK gray encode at baseband and gray decode at baseband. So what's the difference between these two? This one just simply does symbols. It doesn't do anything but the data stream is encoded into symbols, and when you get a symbol at the receiver, you just can say it's an error or it's correct. You can't do anything with it in terms of the actual bits that are underneath those symbols. So when I added the ability to encode or add the gray coding inside of here, I had to put gray encoding in so that I could actually put in my own bit stream rather than just random bits. I can do it on my own bit stream, and then it gets decoded with the gray decoding. So that allows you to do the exact theoretical bit error probability if you want to. Or in simulations I do in COM1 when I've taught it, you could send a PCM encoded speech all the way through the gray encoder, then the decoder, and then you can play it back out through the PCM decoder and actually listen to the speech or whatever.
Maybe this is a random thought, but I guess while we're on this topic, if if you don't mind. I guess an interesting thing about when you're sending integers, right, is that I guess the MSBs have more information than the LSBs.
Right.
Like if you, like a bit error rate in LSB really probably doesn't matter.
That's right.
But I wonder, like,
In speech?
yeah, in speech or probably just in general, right?
Mm-hmm.
So I guess is there a reasonable way to encode, like, to
Yeah.
like, hey, these are more important. I guess I'm thinking from information theory. It
Now
seems
you're
like
right.
something
You're right.
that's
You're
more
absolutely right on the right idea. It's done. It's absolutely done. So, because I worked in speech coding for a little bit as a consultant when I was doing some patent. We were doing some patent stuff.
I guess is that what companding is about?
Yeah, that's what that's about too. But fundamentally, you're absolutely right. And our vocoders that are used in cellular telephony are synthetic speech. So they don't digitize our speech and just send the samples of our speech with the MSBs and LSBs. Instead, those samples in 10 millisecond chunks go through a code book lookup. It's called, the most common scheme is a variant of CELP, Code Book Excited Linear Prediction. So it's called CELP or CALP or whatever. CELP, I think, is how they pronounce the acronym. But so we're estimating parameters from a synthetic model that are in the code book already at the receive end. So you digitize your speech, a code book lookup occurs, and certain parameters, like maybe it's 5 parameters, represent that 10 milliseconds of your speech, and then that can be played back for that little short phoneme of your speech from that CELP table, and then each of those 5 parameters get encoded with different amounts of encoding. Some don't need hardly any, and others need a lot of protection because they're establish the integrity of the speech at the other end. And so the whole idea of synthetic speech is that we can, just like in streaming audio, we can do this, what is that word? It's called spatial, no. I used it in my other class. It's basically messing with our mind.
Right, it's like using
Perceptive
using
encoding.
acoustics to do lossy compression.
Yeah, so it's perceptive encoding and decoding, where you fake it because you can be more efficient that way.
Because you're like, oh, a human can't hear it if I screw this up, and I can send less information.
Yeah. I have Sirius satellite. I'm going to have to quit after this, so I won't show you anything more. We'll wait till next week. But yeah, fundamentally, I see this at work when I listen to Sirius XM in my car. I like to listen to 2 main types of music, jazz and classical. Those are my 2 main things. And classical, I think, requires high quality.
Dynamic range.
Pardon me?
Yeah, I think classical needs a higher dynamic range.
Yeah, and the perceptive coding can't be applied as well without you perceiving it. So Sirius XM has only so much bandwidth, so they play games, and it's kind of irritating at times. I mean, I don't like them compressing that type of material like classical music very much, because you can hear it. You just say, this sounds not too good. Now speech, fine. Certain types of rock music, hate to say it, but I don't think it gets as many bits of perceptual bits. But that's just an interesting topic.
Yeah.
I'm going to sign off and I can say some more.